All right, your time starts now. Okay. All right, so it's going to be about contagion. We're going to talk about some more of these very cool mathematical models. So again, it's understanding very well the details of a well put together model that will allow us to go and understand other things more generally. Plus, this is so we're going to have to concentrate a little bit here. There's going to be some stuff on diffusion. So that's a very simple kind of contagion, but it's a very nice little piece. I need to inject that into your head. So it's a very important, again, very cool little piece for networks. We'll get to assortativity. So we're going to expand our ways of playing with random networks, right? So we've gone from pure random networks to ones with arbitrary degree distributions. Now we'll add assortativity. And then we'll add directions as well, right? So we'll have directed links. And we'll have mixed versions, in fact. So we'll have nodes that, edges that could be of different flavors.
No,
You're throwing things away? Okay, all right. As long as it goes in the right spot. We have chocolate, okay, which can be deployed at. There's two purposes. If it hits you in the head, it can wake you up. But then you put it inside your head, and that will also wake you up. So, okay, so I had a couple of things I wanted to point to about contagion. So this, I think, is just linked to in the paper now. But a great moment in biological contagion was when it really took off. A plague took off in World of Warcraft. It's 2005. So someone made some nasty little spell of some sort. But it turned out it had all these kind of properties of like a lot of real contagion. So it could be, so non-playing characters could get this disease, but it didn't affect them. So they became a reservoir and a spreader, right? So they were a spreader, like, rats would be for plagues, that sort of thing. I mean, so they became a vehicle for the thing to spread. So it spread everywhere, and it really destroyed, there were, if you read this article, there were bodies everywhere all the time. Of course, you can respawn in this game. But you get, it messes you up, but you can respawn, so. World of Warcraft. So it was, and there've been a few things like this. So this is a really, it's actually a studyable kind of pandemic, and it really spread. And you've got all the data. So one of the big problems with real world spreading is it's hard to get the data on who contacted whom and so on. And even if you really go in and ask people, it can be a hard thing for people to remember. But you have to do this, right? If you've got a novel disease in particular and it's just appeared somewhere in your city, someone's come in and they have Ebola, you need to go and tell them, talk to them, who did you talk to, right? And then go and contact them. I mean, it's a very practical thing, but it's hard. Anyway, of course you can do it. Anyway, I just want to throw that. That's a fun thing. So yeah, episodes are adding, right? So I have more pieces here, not episodes, but the actual lectures. So we've got diffusion's going to be here, assortativity, and then we'll get on to thinking about networks that are random networks which have these high level kind of aspects, arbitrary degree distributions, all sorts of kinds of assortativity, mixed kinds of edges, right? So the edges can have flavors, and then we'll think about spreading on them, because that's fun. All right, what else can we do? And eventually we'll get to structure detection. So a number of these things will help for that, like assortativity, for example. Okay, so, but that comes later. So that's just a good little piece. All right. I had more things to show you. Anyway, I've tried to embed a few more things. Obviously, it's contagion. I had a lot more in pox, right? There's a lot more stuff in pox floating around. There's, videos and things. There are all sorts of memes I can throw in here. But I'll build that up a little bit. Let's see. So I was recompiling this thing. Okay, it's recompiled a lot. Nope, don't do that. What else can I tell you before we start? That paper's good. Nope. Okay. All right. There will be 3 new assignments, so that's a lot. But they're 3, they're boxed. Yeah. Okay. 2 weeks probably, right? Because of per request, per presumed request, right? Okay, so here's a good little So the idea is this would have appeared before. There's no real reason for this.
Oh, I just know he's
It's a pangolin. It's a kind of a, armadillo sort of thing spread around a bonus. Because of what?
Man, I hope he walks
Oh,
to the house tonight because I don't want him to.
pangolins have good things in them? Oh no, I mean good things, yeah. Well, just, like the children give it to you, whatever it is. This is infection, right? We're spreading things. Yeah. All right. So the idea is that's a neural reboot. We're a bit early on, but that was supposed to come at the end of the last one. It's kind of enjoying itself. That's mud. All right. It's just playing in the mud. It's not really cleaning itself, I'd have to say. Although you have a bit of grit, kind of good. All right. So, we're at a very interesting time for studying how things spread, right? Because of these traces online, which could be completely artificial viruses like this other one, or or memes and beliefs and all sorts of things that are spreading, right? So I thought I had it here. Maybe I took it away. Yeah. So here's a story. This comes out of some work by people at Northeastern. So it's about interesting thing. I tweeted this actually. Right. That's what I did. So that people who are into certain kinds of conspiracy theories tend to be credulous in general, right? So they'll believe other conspiracy theories more readily. So Cass Sunstein's at the bottom of this saying, that's the best predictor of whether someone will believe a conspiracy theory is they've believed some others. And so they have some kind of interesting examples, right? So where people believe ones that are completely, evidently against each other. So, the idea that Bin Laden, there was a good one with Bin Laden. Maybe it's in this one. Yeah. That Bin Laden, right, he was already dead when the US arrived, and they're more likely to also believe that he's still alive. Right? So these are two different things, but the people are prone to going for things that, anyway. So that's, we have to understand how things spread. So that's a very interesting study. You could look that up. All right. So this guy. We are going to theory. So we saw our pangolin. Okay. All right, so we're going to have to concentrate a little bit. This is, I'm sorry to say. We're thinking about random networks. They have arbitrary degree distributions, right? So this is really fundamental stuff, and it turns out to be extraordinarily rich. What we're adding is the sort of pretty general kinds of contagion processes. That's the thing that's really expansive here, I suppose. But as we've talked about, generalized random networks are, not bad things. They're quite useful. All right. So there are three things we wanted to figure out. So we had, and it depends on the kind of thing that's spreading, but in general, there's this idea of a vulnerable component. So that's the little tinderbox, right? The thing that is a proxy for kind of a critical mass. But it's the case where if one individual in there becomes, starts watching pangolin films, then everyone else will in that group, right? And then outside of that is a triggering component. And so we can think about the probability of triggering. So you've got your little pangolin watchers, and then there are people, if someone out here who is not susceptible to this, but for some reason does watch it, they'll infect this vulnerable group, and it will spread through them, right? And then there's the final size. So that turns out to be a kind of a hard thing. We'll see that there are sort of these flip stories of how to get to these things. Right, this is about expansion. These things are about how things expand away from a seed, or many seeds, as we'll see. We'll actually have an infinite seed sort of story. And this is about contraction. This is actually about contraction. So you're just out there being a human, and this thing is coursing through all of humanity around you. And so it's trying to figure out, you've got all these inputs from your friends and from the media, like when do you switch if you do, right? So that's sort of a contraction, right? So the story or whatever it is. I mean, stories are the great things to think about. This story is floating around in the social network around you and media, and eventually it hits you, right? And you have some resilience to it, perhaps. So we have to think about, will you ever turn on But the first, so there's two flip sides. One, there's these flip versions. One is, the story expanding from a generator type character, someone who starts going, oh, blah, 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 and I bring up the conspiracy one because, of course, now we're in the midst of the Malaysian flight, and there's a ton of different stories. Although it seems to be most recently that searching off into the Indian Ocean off the side of Australia may be the place to go. Which I have to say is a very cold and barren sea, ocean. Anyway, but there are lots of theories floating around. Anyway. All right, so some people are starting those stories, and then some people are out there just waiting for the stories to hit them. They're like, yes, I believe that one too. And some are like, this is all rubbish, right? So that's a contraction kind of story or phenomenon. Okay, so final size. So in these kinds of things, it's very important to think about, we've talked about power law size distributions repeatedly in POCs because they super matter. But in these things, it's usually a bimodal kind of outcome, right? So if the thing takes off just because of what random networks are, and actually most networks, most kinds of basic model networks, it either spreads to some large size or it just peters out at the start. So we kind of understand that overall thing. All right. Okay, so here's the picture. We've seen it. I'll show you again, but the words on the previous page are manifested here. Pictures are always better. So let's see. So that is the first rule of math, right? Is draw a picture, a math problem. Yeah, okay. My first rule. All right. And if you can't, you just leave. Right. So okay, so there's this critical mass. All these people are like, yes, I believe it. I believe it. Thank you. Tell me another story. And so we'll go through them. There are people who are connected to that vulnerable component, which includes the vulnerables themselves, because they're obviously in it. There are these people out here who, say, oh, I think it's this, and then boom, it will spread through here. But it may not spread out to these characters because they're not actually they're not vulnerable. They may take 2 or 3 or 4 hits. There's the overall size, and then there's the final size, which could include it certainly includes the vulnerable component. It could include some of the triggering component, and then some of these people who are not trigger characters, right? They're not connected to that vulnerable piece. So we're trying to find out, sorry about that. We're trying to find out this because this is a condition of whether it can happen or not. This is a condition of what's the probability, right? Because you need to find the triggers. And then this is the final size, like how bad is it going to be? All right, so this is going to be fairly succinct, if I can think about it. But we've done a lot with generating functions now, and you love them. No, okay. We all love them. All right, so let's see. Right. So we want to find this largest component of vulnerable nodes. Okay. So we've already done this treatment where we're looking just at the giant component, right? There was no spreading in that original stuff we talked about when we went through generating functionology. That section, we looked at how to find the largest component, right? And and we figured with our sneaky tricks, and we figured out why things were wrong. So this was the story we ended up with. So again, pi sub n is a probability that if you select a node, it is part of a component of size n, connected component of size n. F of p, so this p is, of course, the underlying degree distribution. Rho is the probability if you jump on an edge and you run along that edge that you see a subcomponent attached to it, including the one you hit, of size n. So we had this composition, right? So the way this worked meant that the distribution for this guy and the distribution for this guy, so you're selecting from this, you're selecting from the degree distribution, you get some degree, and then you say it's k, right? And then you do k samples from this guy, which is the size of those components. You sample from all of them, add them up, and then you get a +1. That's what this generating function structure is doing. Saying, oh, well, and we need +1 because there's I don't have that picture on my slides here. Is that cover this stuff? Should I bring up that picture? I know we've talked about it a few times, but and then over here, this is just the recursion. This is the recursion story for the probably the subcomponent has size n, and so it's composed with its row. The generating function for row is built out of itself, right? So this is and f sub r is that r is again is the probability that you hit a node that it has k other friends. R sub k is the probability that it has k other friends, right? So this is the way these things get built. Again, local stories, global pieces that are being connected through through one step of a local recursion. All right, so we have that. That's just about the giant giant component, but we have to modify it for the vulnerable stuff. Okay, right. So there's some just giant component in here, and the vulnerable component is some part of it, right? So we have to sort of what you can imagine is just take the whole network and then just paint each one that's vulnerable a color, and then just strip off the rest, right? And then you'll have some network that's left. The edges that are still in it, right? So if a node is not vulnerable, that's just taken out, all of its edges disappear. You end up with some version of the original one. And we can actually still use everything that we've done for that. Okay, so it's a node-based percolation, right? Where some guys are in, some guys are out. The vulnerables are in, the non-vulnerables out. Okay, so we had this thing in general. So this is the probability that someone is vulnerable. So there's some threshold distribution, which is independent of the degrees, some threshold distribution. You select from that, and you give this guy a threshold. And then it depends on their k, right? So if the threshold they get is 0.18 and their degree is 5, that means they're in trouble, right? Because 0 to 1/5, 0 to 0.2, they're actually they're vulnerable, right? They're not the other way around. They're not. So if they've got 1, 2, 3, or 4 friends or 5 friends, one friend hitting them, one friend turning on will switch them. Okay. So, and in general, the probability that a node of degree k will be vulnerable will be the integral over the distribution of thresholds up to 1/k. Right. Depends. Yeah. So we're just going to say that we're going to set up our random network, and then we have a distribution of thresholds. We're going to give everyone their own distribution. We've done things where we've said everyone has the same distribution, same threshold, right? But we can also do this thing where we can generalize that. We can say, okay, you can name any distribution of thresholds you want, right? We had some like this, right? So lots of gullibles and lots of stubborn ones. Yep. So if you're assigning these thresholds, you're selecting from this distribution, and you integrate up to 1/k, right? This is the fraction of that population, of the degree k node population that's vulnerable. You integrate from 0 to 1/k, and it gives you some fraction of 1, right? So anyone who got a threshold out here, they're not vulnerable. They have a high threshold, relatively, right? 1/k. Their threshold exceeds 1/k, and so 1/k is the crucial thing. There's 1 divided by k, right? So one of your friends switches on, you see 1/k, and you're like 1/k. Okay, so right, whatever. So you got 10 friends, a tenth. Now you're thinking a tenth of my friends likes Barney the dinosaur, right? And if you're a good person, your threshold is above a tenth, right? But if you're susceptible to purple dinosaurs, then you're in trouble. This is probably when you're 2 years old. Okay, so that threshold, so there's an age tendency for your threshold to leap away. Actually, it's sudden. That's a phase transition. No more dinosaurs. You like Elmo, then you don't like Elmo. It's just kind of true, right? It's like, yeah. Okay, sorry. No, I'm not talking about you personally. I'm just talking about people in general. Yeah. Interesting reveal, but
I never got the Elmo
yeah. Always good, thank you. Well, he's sort of a third person specialist, right? So that's the very young set. They're into the third person. Yeah. Okay, so, all right, so that's an important quantity, right? And we're going to have bkj, right, in general. So j will be 3. That means you know what's the probability that you, what's the fraction of nodes that, what's the probability that you switch on if you have 3 of your friends active out of your k friends? Okay, so we're going to modify our generating function. This is just the simple generating function in here for degree distribution. It's a crazy weird thing we do. We turn it into this function of x. Well, now we're going to compose it. So you've got the probability that you have a degree k node, and then the probability that that node is vulnerable. So this is the probability of selecting, you multiply these two guys together, they're independent. There's the probability of selecting a node of degree k that is vulnerable. So we'll make that, we'll just make a generating function for that guy. So this thing, when we put x equals 1, that usually means what? This equals what? When we say x equals 1. Okay, well, that was a derivative thing. But when just in general for probability generating functions, yeah, it's 1, right? So usually it's, so if we didn't have this guy and you put x equals 1, it's just the sum of pk. That's normally true. So now this is one of these examples again where it's not true because the probability, the overall probability is less than 1, right? Not everyone's vulnerable necessarily. So so we just have to remember that. You can do the same thing that we did before. So if you recall, we found a connection between r sub k and p sub k through generating functions. I mean, we can build it. We can just build it absent generating functions. But we notice later on that it's the first derivative. This r sub k is the first derivative of p. And I'm labeling these both as vulnerable. And then it's normalized. So this one is normalized. It's a bit tricky. So now you're running along an edge. It exists, right? The edge exists. What's the probability that you reach a node? So we've stripped away all the non-vulnerables. Now you're looking at what's left. You're running along this edge. What's the probability that the node you reach is has k other friends that are vulnerable? Right. Think about that. Yeah, because it naturally encodes the fact that you're hitting a vulnerable node. Bit tricky, yeah. How we feel. Okay. So we can do these same kind of functional relationships, right? We have these same things. So we have the pi vulnerable story is going to be related to rho vulnerable through this composition. So again, this is right that the subcomponents. This is rho sub n would be the subcomponent is a subcomponent of n vulnerables, right? And then this is the p that you have a node that has it's vulnerable. Well, that's not quite right. You've selected a node of degree. Sorry, you've selected a vulnerable node of degree k, right? So that's this. So this is this composition. Then you have to do something. You have to do something slightly. You have to concentrate a little bit here because remember this is ultimately some probability of times x to the 0 plus some other probability times x to the 1 plus some probability times x to the 2, and the 1 times x to the 3 is the probability you get a 3. The 1 times x to the 0, which is the constant term, is the probability that you get. Here you go. Is the probability that you get the probability that you get a 0. So this constant term is the probability you get a 0, right? This is a generating function. It's going to be something times x to the 0s. There's an x here, right? So it's x, some blob times x, some blob times x squared, some blob times x cubed. We have to think just a little bit here to make sure that the constant term is all right. So this will be the probability that the guy you selected right? The probability so here's the thing. You're looking at your whole network. You go and select a node from that network. There's a probability that actually it's part of a vulnerable component of size 0. Before it had to be at least size 1, right? It had to be at least size 1 because it's a node. It's part, when we're talking about just the network, you've already selected a node. That has to be part of a cluster that's at least size 1. If it has no friends, that's it. But now you could jump on a node and say, and it's not vulnerable, so it's actually part of a component of size 0. It's a node, but it's not for the spreading event, for this with respect to contagion, it's actually not vulnerable. So it's not. You have found a node that is part of a component of size 0, part of a vulnerable component of size 0. So we didn't have it before because it was actually this. Yeah, it was actually 1. Right, because we weren't thinking about things spreading. Right, so if this is the generating function for, this is the thing I was mentioning before, this is a generating function for the vulnerable nodes for their degree. So that when you set that to 1, you get the sum of the probabilities that you have that you've selected a node of degree k that's vulnerable, of degree k plus 1 that's vulnerable, degree k plus, right, summing over all k. So this is the probability that you select a node that's vulnerable. So 1 minus it is probably you select a node that's not vulnerable. Okay. So it's just it's nasty. So we have a similar thing for the recursive statement for row. Could add pictures to this, I guess. Yeah, maybe. All right, and we have the same kind of thing. So it's going to be the first node that you hit is not vulnerable. So now we're my pen. Right. So before it used to be, well, you're running along an edge, so you're definitely hitting you're definitely hitting a subcomponent of size 1. Doesn't matter if it has no other friends. It's going to be, but it may have others. So this one has potentially edges out to all sorts of subcomponents, but this one might be not vulnerable. Possibly not vulnerable. So so this actually ends, right? This would, if it's not vulnerable, then you actually reach a component of size 0, right? So again, so it's the so it's 1 minus this thing evaluated at 1, right? Which include, right? So because f of r, or just r of k, this r vulnerable thing, it's probably that you reach a vulnerable node that has one other friend, that has 0 other friends, or 1 other friends, 2 other friends, 3 other friends, 4 other friends. It includes that it's vulnerable. So 1 minus the sum over all those probabilities is the probability that you hit a non-vulnerable node. And it doesn't matter how many other friends it has. So there are these two things. One is it's vulnerable and then has 0 other friends, or 1 other friend, or 2 other friends, 3 other friends. This modified version of R goes for all of those. So 1 minus the sum over all those probabilities, I know this is a lot, gets you the probability that this is just a non-vulnerable and the thing stops. Your contagion stops. Runs into a brick wall. So from there you can do everything that we did before, right? So we know what these guys are. They're given to us, they're properties of the underlying generalized random network, and our game is to try and figure out f of rho, which you can do in general, right? We could find f of rho, the whole series, and then we could get, all of the, we get and then plug it in here, and we get f of pi, which we could then get pi of 0, pi of 1, pi of 2 for this vulnerable version, and we'd get the whole story out, right? But once again, we're looking for what's the probability that it's such a probably tricky thing. So it's going to be 1 minus f of pi evaluated at 1, because f of this pi vulnerable. Yeah, but it's for this separate set of this modified generating function. Let me see. It includes Yeah, because f of pi vulnerable also includes the non-vulnerables in it as well, right? Because that's this term. It includes the probability that the first guy is not vulnerable. And then the rest of it, all those next terms are the probability that it's part of a vulnerable component of size 1, a vulnerable component of size 2, a vulnerable component of size 3, which is to say it's part of, more specifically, a finite vulnerable component. So that was this extra piece about here, right? This thing, when you evaluate it at 1, gives you the probability that you are part of a finite vulnerable component, plus that you're actually standing on a non-vulnerable. So 1 minus that is the probability that you're part of an infinite vulnerable component. And that's therefore the size of the largest vulnerable component. So it's a little bit this is a slight, like you're not quite sure, but like this, you have to really think about this, you have to be sure about this, and so on. So there's little tweaks. I think this is probably okay. I needed to deliver it to you. I guess I could give you a question about it. Obviously, you don't want that. But it's all right, right? Oh, good. Here's a meme. Okay. This is one of the big spreads, right? Last year. We only have ourselves to blame. Actually, that was a complete joke, right? This whole thing was a complete joke. This was not supposed to spread. I mean, it was a joke for a well put together thing for a TV show in Norway, right? Should we say something disparaging about Northern Europeans? What's that? No? Okay. Anyway, it spread like crazy. And they couldn't understand it themselves. So, alright. Okay, fine. I think that's all I have to do. But great moments in memes, yeah? I mean, well done, humanity. Really good. Yeah, they were pretty nonplussed, I think. There was sort of interviews where they're saying, well, the Danes will have something about a moose next week and we'll be done, But people who are successful with spreading things early on, it's like going to the casino and winning first time. It's hard to make things spread, right? So you can sometimes be lucky straight off, but it's hard to really make different kinds of things spread. If you're really successful and you've done something that's, people really will, you're a novelist, then that helps next time around, right? So if you're Tom Clancy or whoever it is. J.K. Rowling's a great example now, right? Because she had this book written under a pseudonym that it was okay. It got reasonable reviews, actually. One about a lawyer, I think. She's written a couple of different books. There was one that was very different. It was under her name. Tons of people bought it. It was extremely different to Harry Potter. And then there was one recently which was written, under a pseudonym. And it had been selling not that well. But then it came out who it really was, and of course then it sold a bazillion. Which, is a terrible indictment on people's ability to, what are you doing, humans? Like, you have no understanding of quality, right? Because it's all socially constructed. Well, a lot of it is. Anyway. All right. I think it might have been leaked so they could, someone in the publisher is like, we got to make this. Someone somewhere said, boom. All right. Okay, so we're going to modify this just a little bit to find out the size of the triggering component. So that's sitting around the vulnerables. So it's the vulnerables plus people who are themselves non-vulnerable, but are connected to vulnerables. And it turns out there's a very small change to get this to work. And so this took a few years to figure out. So Duncan actually solved that first part that I showed you. Duncan Watts, who solved that first part for the 2002 paper, PNAS. And then 4 or 5 years later, got this to work. 3 years. And other people saw this. Let's see. And I don't think we ever published this. But anyway, so it's a tiny thing. So we want to find the probability that, what's the size of the triggering component? So we have the largest vulnerable component. What's the size of the largest triggering component? So everything's the same setup, right? So this is exactly the same statement here that we had for the row probability, right? So the recursion statement for row goes through f of r. But we modify this one in the following way. So we don't care what the first one is anymore. We don't care where. So there was this kind of structure, and the other structure we have is, right, there are these subcomponents potentially around some initial guy. And with the vulnerable component, we worried that this one was vulnerable or not to start with. But if it's a triggering component, this guy can just be anything, because we're turning them on, and then they're connected to some vulnerable components. And we're going to measure the size of that component, right? So it's going to be this guy plus all the vulnerable components they're connected to. And it doesn't matter what this one is. So we don't have to worry about this fiddle at the start. It actually goes back to looking exactly like the original equation. It's an f of p, right? That's this composition gives you, right? You're selecting a node, and it has k friends, and now you're going to select from this row of k vulnerable. I guess it's really this. Notation could be fixed. You're selecting from this, but you're going to give it a +1, whatever the case is. You're just going to say +1, and it doesn't matter. The first guy's vulnerable for sure. Or not, it doesn't matter if the first one's vulnerable or not. Right? So you still solve the same equation to get your the row stuff, and then you can just put it in here, and it follows through to here. So it's going to be a bigger amount, well, at least the same size as the vulnerable component. Anyway. So that is how you step out to the, so generating functions, very simple, very clarifying, right? We'll come back to it, and I'll give you some other intuition for how to think about this stuff as well. And it's more intuitive, actually. I mean, it's fundamentally intuitive. All right, so you get the same story. Now it's going to be triggering, right? 1 minus f of pi, triggering. Okay. All right. Right. Because where's our picture? Wow, I have to jump through that Fox thing. We should just be forced to watch it every time. What's that? It's actually only a minute. What's that?
If we're worried about finding the trigger to the largest vulnerable component, why would we ignore the first one?
Because it could be here. It could be this one. Right? So here's the largest vulnerable component. They're all connected together. We can have someone who's connected to that component but is not vulnerable. So what we're doing is we're saying, here's this patch. We're going to include all of these guys now. So everyone in here is a trigger by default, because they're part of the tinderbox, right? True. But they're a triggering, right? But then there are other ones who are non-vulnerable. They have a gullible friend. Yeah?
I like the picture better.
More pictures? Yeah, no, I could carry. It could have been hanging around here. Yeah, right. So, I definitely want two screens. And then you have it all tuned up, right? Like which ones would stay, and clearly what we need. Well, just as you go through it, like there'd be ones that would last on this side, and then these ones would change, and you'd have a whole elaborate. Yeah. I guess just two computers. Anyway, all right. So, so right. So if you switch this one on, right? Here's a new religion they found out about online, and they just talk to their friends about it. All these guys are suddenly wearing funny hats, right? It doesn't really matter if this one does or not. And it may not spread, right? It won't necessarily spread out to that triggering component at all. This is it goes through here. Yeah? They've all got Ugg boots on, right? Now they've, right? And then potentially, depending on the thing, it comes out and starts to get characters who need 2 or 3 or 4 people around them to be wearing Ugg boots. Which once again, I want to say is a mistake. I mean, it's an Australian product, but no one wears them outside. Yeah. Or if you do, you have your packet of cigarettes under your t-shirt. Okay, so certain, yeah. So it's a little hard to watch. All right, okay, so that's it for these 2 things. Isn't that fun? So it's inscrutable, but it's compactly done. I mean, we suffered to get here, obviously, but in the end, it is these. We can write it down in this relatively simple, weird way. All right, but we'll come back to this again. This is just unnecessary. So look at what's happened to us, right? Now we have a periodic table of advice animals, right? Have you seen these things, right? So I mean, these are spread around all the time. It's a particular, here's one. Yeah, for example. So this picture of this cat has, where's the, so wrong, right? Right, so there's just, there are all sorts of, yeah. These things spread spectacularly. Everyone loves this stuff. Grumpy cat, there you go. That's Grumpy cat. Come on. Okay. Right, so it's so bad that now we have a taxonomy. I'm just trying to say, meme taxonomy. I mean, it's obviously made up, but I think there's some effort to get it to work, right? You can look that up later. Meme taxonomy. I mean, super interesting thing to do, to be honest, completely. Yeah, because it connects really to stories. Okay, final size. So this is a harder, this is not a, okay, we're not, no generating functions now. This is a bit of a surprise, right? We sort of, everyone, became kind of almost militarized with generating functions. They're like, they have to strap them on and they get them to work on all sorts of things. And it's like, ha, I know generating functions. I can do magical things with them. Yeah? You don't know what I'm doing. So, so you're sort of hunting around for a solution because you think, we have to use the magic, right? We have to use the magic. This is a strange place. We have to visit this strange place. So it turns out you don't. And this was done by James Gleason and some of his team. He was at Caltech. Now he's at as a graduate student. I think now he's back. He's an Irish lad. He's back at University of. He's in Cork, University of Limerick. I believe that's right. Lovely fellow. Okay, so so we want to find the expected size, and as I said before, it either doesn't take off or it does. And if it does, it goes to a typical size. Right? It doesn't go to some sort of random size. It goes to a typical size. It doesn't go to some parallel size distribution of sizes. Right. So this is not easy. That's the second obvious statement. So it's not obvious. So the problem is trying to think about. So we've managed to say, okay, all right, we can think about the nodes that need one hit. We can just say, all right, let's find all of those and then see if they're connected enough. And that's a plan. It makes sense. We haven't even thought about how it would spread time-wise through them. But if you have 30 characters connected together in some way and all of them need one hit, then you can see that it's going to work, right? Okay. But thinking about these structures when they need 2 or 3 or 4 or 5 hits, and now we're in this the giant component is something we've always danced around. So for instance, if you think about the calculation for finding the largest, the size of the giant component, we do it by finding the sizes of everything else, right? It's a scary thing, right? So you're trying to measure the size of a forest or a jungle that you can't go into because you get eaten, right? Like all your math things, you go, hey, I have calculus, and they're like, no, thank you, I will eat you. So you have to use your calculus outside, and your linear algebra and stuff. You use these things outside. That's all safe. It's all safe. Count one tree at a time, like a little group of trees. That's fine. And then you report it all back to some central thing. Then you can say, well, I know how big the whole thing is. I'm just going to subtract all that stuff off it, right? But anyone who goes inside that forest, which is the thing you're interested in, immediately dies. Okay. So at least intellectually, but it is tricky. But this actually we will run around inside. It's very hard to think about because inside these giant components, and one of the things you just worked on is think about so you've got an infinite random network. How many pure random networks? How many triangles are there, right? So if you have two friends, you're in a random network. The chance of them being connected is 0, right? It's just 0. The thing is just infinitely big. There's just no way they'll be connected. P is vanished away to 0. You've got some average degree, but there will be some, right? And you guys hopefully figured this out, right? So it's what was it? L factorial divided by what do we get? N choose L, right? Times L minus 1 factorial over 2 times P to the L, right? And you take the limit with N and things go away and you get some number, right? You get 13, right? You get 13.2, right? So you make your random network and there are 13.2 triangles. You will never find them. But there will be a giant component. I mean, if it's connected enough, there'll be a giant, right? If the average degree is greater than 1, there's a giant component. And inside that, a really huge, long, depends how connected the thing is, cycles. So while there's a finite number of these small cycles, as you go up through all sorts of cycle lengths, you'll find them, right? So there are these really long. So it's a weird structure. Locally, it's branching, but things come back in that giant component. All of the other little finite components, they're pure branching structures, no loops. That's why we're happy with them. We can count them and enumerate them and put them in boxes and say this is the one, this is the stripy leopard or whatever, right? We can put them very carefully in our little mathematical world. The other one is this nightmare scenario. Okay, so, but somehow we'll get into it. Yeah. Okay, so it's a really great paper. I think it should have been in Physical Review Letters, but so it's. And the framing is more about the seed size, actually, which is interesting. But they figure out the final size. So they're going to put now instead of just starting at 1, now we've got, of course, this is crazy, right? We have an infinite network, and we're going to set off a fraction, some small fraction. So that means an infinite number will be turned on, right? If you have an infinite network and you turn on 1%, then still an infinite number. But they'll be a long way away from each other, on average, right? So again, it's kind of like if you make that initial fraction that switch on very small, it's still an infinite number that gets switched on, but they're very separated. Is that kind of okay? Doesn't help if I do this. All right. And there's some more. So Gleason added a whole bunch of stuff for your modular net, all sorts of other, as we've talked about, complicating random networks. One natural thing is to say, I'm going to have modules. They'll be random inside and then random connections across, so you can do that sort of thing. And that starts to look more and more like certain real things. So these are the 2 papers to play around with. I'm going to give you some problems that, where you actually have to reproduce some stuff that's in one of these papers. So the game is to make the figures, not by photocopying, which is an algorithm, but not the one that I used an algorithm. It's like, all right, iPhones. Okay, so let's try and get this to work. So we're going to randomly turn on a fraction of nodes. So as I said, it's a fraction now. Time t equals 0. We are going to use the branching network structure again, right? So locally, it's always a branching network. So, it can be very well connected. It's still going to be a branching network. And we want to think about this. So, and I was saying this before, right? So you're a good, decent, non-conspiracy believing type person, and you're just sitting out there and the thing is coming, right? So the ones that are setting the thing off are the crazy people. And you're sitting at home saying, that doesn't make any sense and that doesn't make any sense. But, if 33 people tell you that this happened, you're like, oh, okay, right? But how do they get you, right? How do they get you? And there's some really good empirical work now, actually, that gets at this problem, because the more independent seeming those things are, this is something we talked about years ago, but we didn't have any data. It was before Facebook existed. It's like, yes, you get 3 hits, But it's really different if you hear it from, you know, a friend of yours, and then, you know, some sort of random human over here, and then, you know, another, right, on TV or something, and they all seem completely independent. You start to think, well, that's a big deal. That is kind of around, right? Of course, it could all be a horrible trick, but actually, it works. There's really nice evidence now for Facebook adoption that's true. So the more diverse it's actually whether you go on at the start, right? Just whether you just sign up, because of course they nastily they know about you already, and they have email contacts and that sort of thing. So the more diverse your group of people are that are on Facebook already, the better the chance that you will switch on, right? So you could have, you know, 10 million friends from, you know, high school, obviously, you know, a lot of friends from high school, but if it's just from there, that's not as good as having, you know, your whatever it is, your soccer team, your Dungeons and Dragons group, you know, your Star Wars fan club, you know, like, so you've got, you know, that tends to, they're all the same. But that makes it, so there's nice evidence about that now, but it makes sense. All right. I'm trying to get this idea that it's about contraction. Okay, so let's think about how, as time unfolds in this spreading, how it can come about that you switch on. Good, decent, non-conspiracy believer. Well, so you could be one of these maniacs and you're just like, yep, you're in, right, at the start. Yeah? Pass me the electrodes, I'm in. That's a reference to a religion that I might get in trouble with. Yeah. Which one? Scientology, right, okay, yeah. So, I probably won't be here tomorrow. Okay, so let's see, so, I can edit it out, right. Let's see, so, yeah, it's the personality testing. So let's see, probability is phi 0. Right, that's just our standard, that's the probability of switching on. That's what we say, we're seeding it, it's random, that's probably you switch on. So, okay, so it is a little bit weird. T equals 1, well, you're not a seed, right? You weren't a seed, but one of your friends is, and your threshold's exceeded, so you're vulnerable to just that one friend. So that's got to, I mean, maybe you have 2 friends switch on if it's a high enough thing, right? So then you could be someone who's a non-vulnerable. In the first time step, 2 friends turn on, and that exceeds your threshold, and you're in. Okay, so now T equals 2, you know, you're someone who didn't switch on in those first 2 time steps. Now it's the case that you're feeling the effect from 2 time steps from 2 degrees. Right? Not 3 or 4 or 5, but at this point it's 2. So in general, after T time steps, you're feeling the effects from T degrees away from you, which is a long way in a network. Let's keep eating the chocolate, people. So, is it gone? Oh, you need to pass on the, yeah. It looks like it's from City Market, but it's actually from a military surplus. So. Kidding. It's a very tangential community reference. Okay, so suggest you watch Epidemiology if you have not seen that show. Okay, all right. So does this make sense? Like it's coming, and I'll have some pictures. Right? Yeah? So T equals n in general, so it's got to be people who are n hops, n degrees away from you. All of those people now have an effect, right? So the first row had a chance to get you straight away. The second row has a chance, their effect is coming in. They may have switched. You know, ultimately, it's all about the row just around, or the your friends, right? It's all about your friends. I mean, they're the ones you're connected to, but they've been feeling effects from outside as well. All right. How do we feel about this? Okay. We have 2 ridiculous drawings because I made them. I kind of want to, I don't know why I should, but let's imagine everyone has a threshold of 1/3. And so this is going, so this, right, that one of their neighbors was on straight away. They have 5 friends, so 1 out of 5, so they're resilient to this. Like, no, they're not good. All right, and then we look at this. This one has 3 friends. 1 was on, so now they're on. This one, so we go back. This one was on already, this one was on. So this one switches on, again, a 1 in 3. So this one here, we'll see 2 out of their 4 friends. This one only has 2 friends, so they're just hopeless. It goes boom, gets them, and something else. And I'll show you a more ridiculous one on the next slide. This one actually gets it now as well, because they just have one friend. And they're like, sure, whatever you're doing. And can I do it too? And then this, boom. And so now it's 2 out of 5, it's 40%, exceeds 33%, and so this one switches on. But this is the thing we have to turn into a mathematical equation, essentially, or a pair of mathematical equations. Again, it will all be about edge transitions. So I think, one of the big general stories for thinking about networks is that we like to think about nodes because we're nodes, we're things. But it's the edges that really matter, right? That's where the stuff happens. Yeah. Certainly, when you think about spread, it's the edge, it's where it gets communicated. But analytically, that's true as well, right? I mean, obviously, it's a coupling, but analytically, it's where you really get traction. All right, so xfig. This is xfig. Let's enjoy this. Okay, so this was the first one was an attempt to kind of explain this. The second one is a little bit better because it's ridiculous, and it also has colors for when they turn on, right? So, right, this one has what do they have? 9 friends. Yeah, so they need 3 or more to switch on, and then they'll go. So you can follow this through. It should work, right? So they had 2 friends, so they switch on. 2 out of 4, this one switched on. These ones are more resilient. Actually, you can see how many friends they have out here. This one, so when this one went back this way, right, it's going to get this one next as well. Actually, so it's going to spread off in that direction. But we're not interested in that. Somehow we have to cope with that as well. Like the fact that it might go back that way. Once this is on, so this is crucial to these models. There are some refinements later on that deal with this. These, once they switch on, they're on, right? SI models, susceptible, infected. Once they're infected. So that would be, that you can see that would create complications, right? You'd have to account for the fact, right? So you've got 1 out of 9. You need 2 out of 9, you need 3 out of 9. You want to see those things grow. But if this one could switch off, they're like done with it, then that's dangerous, right? For your calculations, not for the real world. Let's see. So now we've got a new, right? So again, these ones are susceptible. So this is a non-vulnerable, right? So they needed 2 out of 4 because the 1 out of 4 wasn't enough. So in the third time step, they turn on. Again, the same story here, right? This was on initially. It doesn't change, but it changes now. It's these 2 out of, that's dash. Yeah, 2 out of its 4 friends. And then in the last one, we have this, right? So again, these guys, so that was a 1 out of 3. This is a 2 out of 4. So they're somewhat resilient. And of course, this one was very resilient, needed 3 hits. It actually got to 4, so it switched on. And again, cascading this way.
In the middle, right next to the black center one, the blue one on the right turned on when there were only 2 neighbors, 2 green neighbors that were on.
Yeah, so here it has no one's on.
Yeah.
And now suddenly it has 2 out of 3 friends on. So that exceeds its threshold.
Oh, a time T. Okay.
Yeah. Yeah. Everyone is special. So yeah, right. So good. Yeah. Hopefully this is right. And then switches on, and now it gets okay. Yeah. So we have to account for this, right? So this one switching on here traces back out to this branching network out here. Right? So we have to march out from there. Right? To get to this one switching on, we have to figure out what's the probability that at that time, what's the probability that it got that it was, and we have to account for all the possible configurations that guy could see going out this way, because right, these are random networks. So this is a random, these edges are random. They can go to random subcomponents. So we have to think about all the possible structures that could arise. So we're going to enumerate all of those. All right. There should be an if. Right. So if. So If model, right, if the nodes do not become inactive, right, there's no way of them going back. That's a strong, and as I said, you can, I should reference an improvement on that. Right, typical kind of thing, you solve something, you relax some assumptions, or you add more complications. Again, as we've sort of said through all of these courses, that you solve you do as well as you can with basic models, and then there's sort of a limit. You don't want to you could just keep adding things, and people will do it, but no one will care. You just had some fun with math. Like, it doesn't help anymore. And you're kind of into this in-between world where you're not really, there are so many things you can add at the next couple of levels. There's the essential model, or kind of an essential model, and there's just a bazillion different, adjacent models you can explore, which gives, people careers, but yeah, they shouldn't do it. All right, so this is not just for the threshold model, which I've used to show that works for all sorts of, really contagion processes in general, as long as they switch on and stay on. And in fact, it's not just the final size. We're actually going to see how the thing infects with time, right? What the expected fraction will be on at time t equals 7. We'll actually get that, which is pretty spectacular, in fact. Very, very unexpected for this model, I have to say. Like, getting the final size seemed to be, like possible, hard, but possible. Okay, it's going to be, all these guys are going to get infected at some time, time t equals infinity. But in fact, this calculation will get the whole arc to the detail of, nodes of degree k. This fraction of nodes of degree k will turn on at time 17, right? It's quite specific. Okay. Yeah, that is in fact what I just said, right? Okay, so you can deal with asynchronous updating, which is another good complication, right? You can get very different things can happen if you have synchronous or asynchronous updating in models. You'll be very careful with that. Okay, and this is sort of this thing I've said, and now we have a picture. This is taking off, right? We think about how things spread away from here. It's a bit opaque in the generating function story, but it really was this. We had the pi of n was about here, and we connected it to a row of n's out here. We'll have a better, more, work actually that came out of this course. We'll have a better story for how this can be computed without generating functions coming. And then thinking about the size of it. So this is about whether it takes off, the probability it takes off, right? The possibility and then the probability. Then the final size is about this kind of view, right? Those evolutions I just showed. It's about whether, right? This could be a quite resilient character. Like, we can really think of them just one at a time. We'll say, okay, here's a node that takes 7 hits and they have 13 friends. What's probably they get hit at time, they turn on at time t. So this will be, and we again get to harness this branching network story. We don't have to worry about big loops. So expansion and contraction, really nice. This is really nice. It's really nice. Okay. So let's set this up. Let's set up the start of it. I'm going to talk about maybe another 10 minutes. Okay, and so we'll set up the start. All right, so this is what we want. We want phi. We're going to have phi for the probability. So it's a probability, or it's the fraction, of nodes of degree k that are on at time t. So they could have been on at time t, before that. And then we need to think of how this gets incremented or increased. It's never going to go down. It's always going to go up. We'll stay the same. So we've had this notation before. We had just had bk1, but now we're going to have bkj, right? So it's a degree k node. What's probably that it gets switched on when j of its neighbors are on. And so that's just it. That is the property of the contagion model. Whatever the contagion model is, you have all sorts of elaborations for the contagion model. You turn them essentially into this matrix, like a upper or lower triangle matrix of probabilities. Right, so you can have all sorts of mechanics you talk about, but eventually you have to turn it into this. Okay, So we start off, it doesn't matter what your degree is initially. Again, we could tune this in some way, we could change this, but for this model, we're just going to sprinkle infecteds around with probably phi 0. So the initial fraction is phi 0. It's also the, you can think of it as, it's also the probability that as you go to each node, you switch it on or not. Put a pair of Ugg boots on it, right? Okay. And it's phi k of 0, so time equals 0 independent of k. All right, let's think about these pieces. So around a node, right? We've sort of had sketches of one person being switched on around in a local neighborhood, but you could in principle have all of your friends switched on at time 0, whatever, or none. Yeah. So we're going to have this guy here. Let's make them okay, like there's nothing changed. So this one switched on and this one switched on, right? So what's the probability that, this here it's 2 out of 6 are on? Okay, so the way we write that down is to say, well, there's 6 choose 2, or k in general, k choose j ways of having j of your friends, choosing j of your friends as being on. They have to be on, they'll be on with probably phi 0 j. And then the rest of them will be off with this probability, right? So k minus j other friends, so they all have to be off. Right, so if you sum over j, from j equals 0 to k here, you get, 1.
So they're seated and they're on?
If they're seated, they're just on. Yeah, yep, they don't turn off. Is that what, yeah? Yep, they're just on. And so this is just in your first neighborhood, right? Right. What's the probability that j of them are on? Well, you have to have j on, the others have to be off, and then there are k choose j ways of choosing j people to be on. Okay? So the extreme is j equals 0, none of them are on. That means this guy is just a 1, and then all of them failed, right? They failed to switch on. So this is to the power of k. At the other end, k choose k is 1. They all switched on, so it's phi 0 to the k, and then this piece is 1, right? Okay, so standard little combinatorial probabilistic piece. We also have to account for the fact that this guy could have been on at time 0, right? So there's the fact that they could have been on at time 0, so we just account for that. There's probably, because we're trying to figure out if they're on at time t equals 1. They could have been on at time t equals 0. If they weren't on at time t equals 0, then we have to think about what happened in that next step. And it's only about their friends, right? Okay. Okay, so they're off to start with probably 1 minus phi 0, right? And then let's put it together. So this is the probability that a degree k node at time step 1 is on. Well, it could have been on, right? Time 0. So it's already on, and if that's true, we don't worry about, we're not going to compute anything else. And the way to think about that is we'll say, all right, well, what's the alternative, right? So in the probability this is the probability they weren't on in the first time step. And then here's the probability that they switched on in that, because of that first round of friends. So it could have been that they had j friends who were infected, and then we need the probability that j friends switches them on. We'll see the case that j equals 0. You could have bk 0, not 0, right? So it could be that you are just, I love it. I'm just going to be in. I don't care what my friends say. this is what I do, right? So I'm with the dinosaur thing. So this is just your on. So that will allow for that as well. So that's possible. Does that work? That's interesting. Maybe that's not quite there. Okay. All right. So does that look okay? That little construction is just one time step. And it's, you pure branching network. It's okay. You don't have to, right. Yeah. And we've already specified that it has k friends. So we don't need p of k in here. It's just k friends. Is that Okay, so for general T, right, in this picture we're trying to draw, this incoming thing, for general T, we need to know what the probability is. So now we're at many time steps. We need to know what the probability is that one of your friends are on now. And so you can think of these edges coming in as being from random worlds outside you. What's probably that this edge has finally switched on at that time, or is on at that time, right? It's active. So we had phi for the total. So theta is going to be the probability that an edge is active at time t. And because we have nice random, right? This is a random network. All these thetas should be it doesn't matter where you're coming from. Right, so let's get this guy to work. So we already know that this has to be true. So theta of 0, the probability that this edge is active, is equal to the probability that that guy's active. So theta of 0 and phi of 0 are the same. All right, so the probability in the first time step that you see an active edge, right. So we have a similar kind of story. There's going to be a slight modification, but it's a similar kind of story. So we're going to change it, right, for the t equals 1 case. So the probability that a specific node I, now we're not talking about nodes in general of degree k. This is a specific node. So we're looking at this just as we did with the picture. It's one node in particular. The probability that it's on at time t plus 1. Well, there's a probability that it was on at the start. That's just done. If it wasn't on at the start, there's the this computation, which again, so this is the probability that its edge, that there are j of its edges are on. Now we're thinking about the edges. Before we put, before we were able to put phi of 0 there, it's just one step, we're able to put phi of 0 there because it actually equates to the edge being on, the edge being infected. Really, we want to think about edges in general. This is about whether an edge, a random edge in the system is on. Okay, so j of the edges coming into your on, ki minus j are off. There are so many ways of doing that. And then this is the probability that you get switched on by j of your friends being on. So this is the step up to time t. And then if you want to find it in general, we can average over all nodes, right? So we average over all nodes. So everything is the same. We've really just taken the sum of pk and kind of applied it to both sides. This is really phi, but we've applied this in general to both sides. The sum of pk is just 1, just goes away. Sorry, so it goes away around this piece, but sum of pk pki will give you the total fraction that are infected. That's what we're after. And then we're going to combine it in a way, it was pki. So now we're going to combine it so we get this. I don't want to change it. Okay. So everything is the same. We've just put a sum of pk here, basically. Right, we did it at the individual node level or the by class, by degree k. Fine. If we do it by class, degree k nodes, they look like this. And then we're going to sum over all the, what's probably that our first node has degree k. So, right, this is probably the degree k node is on, if we're focusing on it. Then we sum over all the probabilities of, right, that first node has degree k. So that will give us the total that are on at time t plus 1. No? Nasty? Nasty. Not nasty enough. Okay. Right. Let me get to the next equation, and then the next set we'll kind of explore what happens. So we're very excited. Okay. Well, I know you are. Okay. So we need. So this should look. This is really, again, it's very akin to the whole generating function story where we figured out rho connects to rho, and then rho gives us pi, right? So rho was for the size of a subcomponent. Pi is for the size of a component, right? So it's if once we have the thetas of thetas, we can figure out what phi is straight away, right? So the stuff, once we understand the edges, we get the node stuff. So we need to connect, we need to figure out how the edges work. So now we're going to move to this picture. Now we're going to think about this guy. Let's say this is theta 1, right? It's time step. After this guy has some friends. You know, maybe some of them are on, whatever it is. They have some theta 0 here, theta 0 here, theta 0 here, right? There's some probability that these guys were on. What's probably that this is on? So we're going to think about that transition. So there was a time step 0. Some of these guys were on. This one could have been on. And then theta 1, whether this edge is active, meaning it's coming out of an infected node, well, you can think of it as being dependent on these edges. So it's going to be edge. Right, we're crossing a node. We're taking infected edges to potentially infected edges to another potentially infected edge. Right? Our story will be trying to connect edges to edges. Right? What's probably of an edge infection. So it looks very similar. So the probability that this edge is infected. Well, this guy could have been on at the first time step, so that's phi 0. If that guy wasn't on, then we have this structure, which looks very similar, but it's an edge story, right? So it's a probability that this node that you're connected to has k friends, has k other friends, right? This is r sub k. Kpk divided by the average degree, that's r sub k. So this is probably that this guy has k other friends. Oh, sorry. Probably that it has k friends. Probably it has k friends, meaning it has k minus 1 other friends. And then we have to think about its k minus 1 other friends. Well, j of those could have been on, and there's how many ways we can do that. This is a probability that those guys are in fact on. This is a probability that the rest of them are off. And this is the probability that this node, which is of degree k, given j inputs, will switch on. Right? We're thinking about whether this guy switches on. It's got k friends total. It's got j inputs coming into it from this side. Could be maximum k minus 1. And, right. And so these are all the bits, right? So we have, right. So again, it's r sub k. It's the probability that edge connects to a degree k node. This gives us the probability that, this piece gives you the probability that it activates. I really like that degree node k activates. All right, we're nearly there. Hard. Yeah?
Are we just thinking about it as if edges could be infected, or are we saying edges are infected?
So an edge is infected in that it comes from someone. Yeah. So
Infected node.
that's a definition. Will be. Yeah. So if we jump on an edge and look, we have to look one way. And if we look in that direction as an infected node, then we think of this edge as being infected.
Is this all with uniform thresholds?
No, so it could be anything. Yeah, that all gets folded into this little guy here, BKJ. It doesn't have to be thresholds either. It can be anything. So it's just if you can encode your contagion process into you have k friends, j of them are infected. So however that works.
And that's exactly J friends, like
It's exactly j friends. Yeah. So because you do j and then j plus 1 and then j plus 2. Yeah. That's right. That's right. So, for example, if it is a hard threshold, and then maybe it's 13 friends as your threshold, then 14 and 15, they're all probability 1. But the way this thing has been built up, you'll have had 13 friends have turned on, now you switch on. A 14th comes along, that doesn't change anything. You still switched on. 15th one. Yeah, so you only count that first. What you can think about whether BKG needs to be monotonically increasing. I'm trying to. Sure. Okay. So this was just actually one step. We can generalize this again like we did for phi, the fraction that are on, right? And here are our two equations. Okay, let's look at this. Okay, so the first one is about edges. So an edge coming in at time t plus 1, this edge here, in principle depends upon all the stuff that's happened out here. But we can connect probably the edges over here were on in the previous time step. Right? We can kind of just do it recursively. So, well, for a start, all along it could have been on because that node switched on at time t equals 0. That's always there. If it didn't, then there's this recursive thing that says, well, what's the probability that it switched on in this last time step because it has these inputs, right? It has k minus 1 inputs coming in from the outside. Here are all the possible ways they could be switched on. J of them could be switched on such that we actually get, right, J is switched on properly, and then that's the infection probability. We sum over this because this is how we connect out to nodes. And the initial condition is that theta of 0 is phi of 0. But if you look at this, phi of 0 is specified. This is specified. This is specified. So we put theta of 0 into here, and we get theta of 1. We put theta of 1 into here, and we get theta of 2. We put theta of 2 in here, we get theta of 3. So this actually just is a little machine that maps it up. Right? So it's a map of the interval, actually, like the chaos kind of things. It's a map of the interval, right? Theta is between, this guy's between 0 and 1, sends it to something between 0 and 1. Okay. And then, very similar, in that kind of same way, it's edge to edge here. This is now going to tell us about, at any time, actually, we take whatever the edge probabilities are and compute the probability that a node in particular is infected. Because this is just about getting to this edge. Now we want to know if this node is infected, we have to find the sort of terminal result of all of these inputs. Okay, so it could have been on at the start. If it wasn't on at the start, well, what's probably that it had degree k? And if it has degree k, it could have j nodes on. That happens with this probability. The rest are off with this probability. These are how many ways it could have j nodes chosen. And that's the probability that it turns on with j friends on. And so you sum over this. So these are the social effects. This is the exogenous piece, right? That's done at the start. Social, exogenous. All right, so I'm going to start. We'll use. So now we'll go into some pictures. We'll try to explain this. We'll see it for some strange kinds of configurations. Opens things up in all sorts of ways. That'll be the next exciting piece about contagion. All right. Yeah. All right. Eat chocolate. 15 minutes.